Okay, so in this video we want to look at the differentiation of circular functions. So y equals sine x, y equals cos x, and y equals tan x, and then obviously applying chain rule, product rule, quotient rule to deal with combinations of those and other functions. So here we have the graph of y equals sine of x, and so again, like we have for our previous functions, I want us to sort of think a bit intuitively about if we were to sort of make a rough sketch of the gradient function, what would that look like? Okay, so we know when we're thinking about the gradient function, one of the most useful points is where we have any turning points, because we know the gradient of this function at pi on 2 is 0, and so therefore the gradient function would have an x-intercept at that point, and same at this other x-intercept at 3 pi on 2, at the other turning point at 3 pi on 2. Okay, and so then before pi on 2, we have positive gradient, okay? Sort of steeper positive gradient, gradually getting less steep as it approaches the turning point, okay? And between pi on 2 and 3 pi on 2, we have negative gradient. It's at its steepest at pi, okay, so that was where it'll be negative gradient with a minimum at pi, okay, and then it's getting less and less steep back to the turning point. And then after that we have positive gradient. And so we might speculate that we're going to have something like, okay, in terms of a rough shape, in terms of the actual size of those gradients, I don't really know. But what we're certainly seeing is something that looks like a cos shape. So derivative of sine of x, we might predict would be equal to cos of x, based on just thinking about the derivative graph. Alright, so let's think about the derivative by first principles. Now this, I've worked this fully through because it uses a number of things that we don't know about. But if f of x is sine of x, then f of x plus h is sine of x plus h. So the derivative is the limit as h approaches 0 of sine of x plus h minus sine of x all over h. Now, in trigonometry, we have these things called trig identities, which are studied quite a lot in specialist maths. So it's possible to write, if we have sine of a plus b, that's the same as sine of a times cos of b plus cos of a times sine of b. And so in this case with sine of x plus h, that's the same as sine of x times cos of h plus cos of x times sine of h. Okay, so when we do that, again like we've done previously, let's think about, now I did some reshuffling here in one step, so I'm thinking about grouping that and that together and taking out that common factor of sine x, and so that's how I've got to here. Common factor of sine x leaves me with cos h minus 1. And then we've also got that cos x plus sine h happening there. Okay, so we're splitting it up into two separate fractions, sort of dividing it down the middle here. So we've got sine of x times cos of h plus 1, sorry, cos of h minus 1 over h, so that's all that happening there. And then we've got, I'm thinking about just taking out the cos of x separately because it's got nothing to do with h, times sine of h plus over h. And we're still taking the limit as h approaches 0. So when we do that, limit as h approaches 0 of sine of x, it's got nothing to do with h, so it's just sine of x. When we take the limit as h approaches 0 of cos of h minus 1 over h, we get that. We can think about that in a minute. In the second bracket, limit as h approaches 0 of cos of x, well, it's got nothing to do with h, so it'll still be cos of x. Limit as h approaches 0 of sine of h over h gives us limit as h approaches 0 of sine of h over h. Now, we don't have any fancy algebra for working these out, but over in this blue table on the left, and I apologise, it's slightly cut off on the right-hand side, the printout was a little wide. But what we're seeing here is, here's our values of h. If we, as we make h smaller and smaller and smaller, okay, so as h approaches 0, we can see that numerically working out the value of sine of h divided by h, that value gets closer to 1. So, so that is, this one is going to equal 1, okay? What we see happens as h becomes smaller and smaller and smaller, for the other fraction, cos of h minus 1 over h, that seems to be getting closer and closer to 0. Okay, it's getting close to 0 from below, but that doesn't matter. So this here is going to get closer and closer to 0. And so therefore we get 0 and 1, okay? And we see that the derivative is indeed cos of x. Okay, so we've established that if y equals sine of x, dy dx is cos of x. Alright, let's think about cos. The graph of cos of x is shown opposite. Let's think about what the gradient function would look like. Alright, so the difference here is that we've got a turning point at 0, so that would be an x-intercept on the gradient graph. turning point at pi, that will be an x-intercept on the gradient graph, and a turning point at 2 pi, that will be an x-intercept on the gradient graph. Between 0 and pi, we can see we have negative gradient, with the steepest negative bit happening at pi on 2. And then between pi and 2 pi, we have positive gradient, with the steepest positive gradient happening at 3 pi and 2. And so we've got something that looks like this happening here. So that looks like a sine curve, but it's not just sine of x, it's reflected in the x-axis, so it is negative sine of x. Okay, so as I said, it's purely speculation, and we're estimating what we think it might be. And so what we can actually do is use that we now know what the derivative of sine is, we can use that to work out exactly what the derivative of cosine is. Okay, so if we remember the Pythagorean identity, sine squared plus cos squared is equal to 1, which tells us that cos squared is equal to 1 minus sine squared x, and therefore cos x is equal to the positive or negative square root of 1 minus sine squared x. So if we differentiate that, we should be able to find our derivative of cos. Okay, so let's think about what we've got here. So we've got the derivative of plus or minus 1 minus, now I'm going to write that sine squared x, because remember that means sine of x squared. We've got that to the power of a half. So we're going to need some chain rule here. Alright, so again we're thinking about sort of covering up our inside function. The plus minus out the front is just plus or minus 1, it's just a number, so it's not changing anything. So half, it would be plus minus half times that red section to the power of negative half, and then we need to times by the derivative of the red bit. Okay, so we're going to get plus or minus 1 half, so losing the d dx because we're taking the derivative now, plus or minus 1 half, 1 minus sine squared x to the negative half, and then we're taking the derivative of 1 minus sine x all squared. So derivative of 1 is just 0, derivative of sine x squared, so now we're looking at derivative of this bit, just the sine x squared, and that is going to need the chain rule as well. So we get 2 times sine of x to the power of 1 multiplied by the derivative of sine of x, which we learnt previously was cos of x. Okay, so let's have a look at what we've got here. So here we have, that's at power of a negative half, so it's 1 on the square root. So we've got essentially 1 over plus or minus 2 root 1 minus sine squared x. And then here we've got 2 times sine x times cos x. Okay, so our 2 and our 2 there are going to cancel down. Now plus minus 1 minus sine squared x is cos x. Okay, so this is 1 on cos x multiplied by sine x. Oh, sorry, I lost a negative somewhere. Ah, yes, here. So, sorry, there's a negative there. So when we took the derivative of the inside, that should have been negative. So this is still negative. This is still negative. Sine x cos x. Alright, so our coses are going to cancel out, and we just have negative sine x. So the derivative of cos x is indeed negative sine x. Alright, so, sorry, if y equals cos x, dy dx is negative sine of x. Okay, so now we can make use of the derivatives of both sine and cosine to determine the derivative of tan, because we know that tan of x is sine x on cos x. So if we use the quotient rule here, and what we know about differentiating sine and cos, we can find a derivative for tan. Okay, so quotient rule, we differentiate the numerator, derivative of sine is cos, we leave the denominator as it is. We subtract, we leave the numerator as it is, and we differentiate cos of x, the denominator, which is negative sine x. And then we have all of that over the denominator squared. Alright, so we have cos squared x, it's cos x times cos x, and then we've got plus because it's minus minus, so plus sine squared x all over, well, we can write that as cos squared x on the denominator as well. Now, again, let's remember our old friend the Pythagorean identity. Sine squared x plus cos squared x is 1. So that's the numerator of this fraction, sine squared x plus cos squared x. So we have 1 over cos squared x. That can also be written as, so I'll write that in the box here, y equals tan of x. If y equals tan of x, then dy dx is 1 over cos squared x. Okay, and 1 over cos squared, or 1 on cos, is actually something called a different trig function called sec. Okay, so if we have 1 on cos squared, which is the same as that, we have sec squared x. Now you don't need to know about sec. They are called the reciprocal trig functions. 1 on cos is sec, 1 on sine is cosec, and 1 on tan is cot. You don't need to know anything about them. You are welcome to just always write your derivatives of tan x as 1 on cos squared x. But 1 on cos squared x is the same as something called sec squared x. Okay, so if you see the answer written in that way, understanding that 1 on cos is the same as this thing called sec. Okay, so let's use the chain rule to help us differentiate the following. Alright, so we've got all our derivatives listed here. So we know derivative of sine x is cos x. I'm going to work across for a bit here. Derivative of cos x we know is negative sine x. Derivative of tan x we know is 1 on cos squared x, or sec squared x. Alright, so then if we have sine of ax, so I don't want to do my long-winded chain rule. Let's think about, abbreviated chain rule. Let's think about cover up your inside function. So derivative of sine of something is cos of that something, and then you multiply by the derivative of ax, which is a. So what we're actually going to get here is a times cos of ax. And that will follow through the others as well. This will be negative a times sine of ax. This will be a times cos squared, a over cos squared of ax. Okay? Or, so this would be, we could also write this as sec squared x, or this would be a times sec squared ax. Same thing. Okay, if we have ax plus b in the functions, so sine of ax plus b, so again thinking about chain rule, cover up your inside. Okay, so you're going to have derivative of sine of something is cos of that something. And then you're going to need to multiply by the derivative of the inside, the derivative of what I've got highlighted in blue there, which is a. So we're going to write this as a times cos of ax plus b. Okay, same for cos. Negative a times sine of ax plus b. Tan, again it will be a times, cos squared ax plus b. Or that's the same as a times sec squared of ax plus b. Okay, so generally speaking then, sine of f of x, okay, so again, covering up your inside function, you've got sine of something, derivative of sine of something is cos of that something, and then we multiply by the derivative of that highlighted section, derivative of that inside function, which is f dash x. So we're going to get f dash x times cos of f of x. Following that through with our other functions, we're going to get negative f dash x times sine of f of x. And here we're going to get f dash x over cos squared of f of x, or f dash x times sec squared of f of x. Okay, so there's your summary, but I don't want you to feel that you need to be remembering 12 different rules here. You've got your 3 basic rules. What is the derivative of sine? What is the derivative of cos? What is the derivative of tan? And the others are all just applying the chain rule. Okay, so you can just think through the chain rule each time. Okay, so a couple of notes. Obviously, we've used some of these things along the way. So the notation cos squared x is an alternative way of writing cos of x squared. So it's important to think about that because it's going to require the chain rule when you differentiate that. So it's helpful sometimes to rewrite them that way so you can see what's happening. Your CAS does not understand cos squared x. You cannot enter that expression in. It's a meaningless mathematical expression. It's a really misleading notation. Okay, you can't square cos. Cos is an operation. It's a function. It's like squaring addition. It doesn't make any sense, okay? So it is cos of x all squared, and if you're going to enter that expression in your CAS, you'll need to actually type in, yeah, cos of x all squared. The reciprocal of each of the three trig functions are themselves trigonometric functions. So the secant of x is sec x, which is 1 on cos x. The cosecant of x is cosec x, which we abbreviate as CSC, which is 1 on sine x. And the cotangent of x is cot x, which is 1 on tan x. You do not need to know those. The only reason we're bringing them up is because this one on cos being sec comes up a bit when you're differentiating tan. But as I said, you can always write it as 1 on cos squared and forget completely about sec. Okay, let's work through some problems. To differentiate each of the following with respect to x. Alright, so dy dx, we've got sine of 3x, which is the simplest version of the chain rule. It'll be derivative of sine of something is cos of that something, so cos of 3x, and then we'll need to multiply by the derivative of 3x, which is 3. So we'll get 3 times cos of 3x minus 2 times, now remember that 2 doesn't do anything, doesn't change the derivative in any way. We're differentiating cos of 4x, which is going to be negative 4 times sine of 4x. So derivative of cos of something is negative sine of that something, so negative sine of 4x, and then multiplying by the derivative of 4x, which is 4, which is how we get the 4 out the front there. Alright, so we've got 3 cos of 3x, and then we're going to have plus, because we've got minus 2 times minus 4, 8 sine of 4x. Okay, B. Again, we're going to need the chain rule here. So we've got cos of something, okay? So derivative of that, derivative of cos of something is negative sine of that something. And then we're going to multiply by the derivative of that something, which is going to be 6x squared minus 10x. Okay? We would normally write that at the front to avoid any ambiguity about whether or not it is actually in the sine function. Okay? So we would write that as negative. You might also take out the common factors there of 2x, which would leave us with 3x minus 5 times sine of 2x cubed minus 5x squared plus 1. Okay, y equals sine squared 5x. Okay, so remembering that this is sine of 5x all squared. So we're going to need the chain rule. dy dx is going to be, so thinking about something all squared, so that's going to be 2 times that something to the power of 1, and then we multiply by the derivative of the inside. Derivative of sine of 5x is 5 cos of 5x. And so we're going to get 10 times sine of 5x times cos of 5x. Now there is actually a trig identity that would enable that to simplify further. So you might find occasionally when you differentiate trig functions using your CAS that it gives you an expression that's not what you expect or not what you would get by hand. And that's just because sometimes it utilises the various trig identities to further simplify your expressions. But this is perfectly correct in terms of having differentiated. Okay, part D, y equals x times cos x. Again, this is the one where you're going to miss that you have a product. You have a simple linear function multiplied by a cos function. So you need the product rule. So dy dx, product rule says we differentiate the first function, which is going to be 1. Derivative of x is 1. We leave the second function as it is. We add, we leave the first function as it is, and we differentiate the second function. Derivative of cos x is negative sine x. So this is going to be cos of x minus x times sine of x. Okay, part E. Y equals log e of sine of 2x. Okay, so we've got chain rule here. We've got a sine function inside a log function. So thinking about it as derivative of log e of something is 1 on that something. Okay, and then multiplying by the derivative of the inside. Derivative of sine is cos, and then we'll also need to multiply by the derivative of 2x, which is 2. So we're going to get 2 cos of 2x. Alright, so we've got two lots of cos 2x over sine 2x. Now, you might recognise that, that's fine. Again, you've differentiated. We know that sine on cos is tan, which means that cos on sine is 1 on tan. So this is actually going to be 2 over tan of 2x. Okay, part F. Again, thinking about, you're going to want to use the chain rule here. You've got tan of 3x all to the power of a half. Okay, so derivative is going to be half tan of 3x to the minus a half multiplied by the derivative of tan of 3x, which is going to be 3 over cos squared 3x. So derivative of tan of x is 1 on cos squared x. Derivative of tan of 3x is 1 on cos squared 3x multiplied by the derivative of 3x, which is 3, which is where that 3 on the numerator comes from. Alright, let's think about what we've got happening here. So we've got negative half, so this bit here is 1 on 2 root tan 3x multiplied by 3 on cos squared 3x. 3 over 2 root, in fact I might write the cos squared first, just again to avoid any ambiguity about whether or not the cos squared is under the square root. Often best to write the square roots at the end. Sorry, that's tan of 3x. Now, you probably could simplify a little bit more in thinking about that tan of 3x is sine of 3x on cos of 3x, but given that it's under the square root, it's not going to simplify very nicely. You're going to have fractional powers on everything under there, so I would probably just leave it at that. There's nothing wrong with that. You've differentiated as it is. Okay, part G here. Y equals f of x divided by sine of x. Okay, so we have a quotient of two functions, an unknown function over a sine function. So we're going to need the quotient rule. So dy dx, we differentiate the numerator, that's f dash x, and we multiply it by the denominator. We subtract, we leave the numerator as it is, and we multiply that by the derivative of the denominator, which is cos of x. And we have all of that over the denominator squared, which I'll write as sine squared x. Now there's not going to be anything more we can do with that. F of x and f dash x, not common factors. Sine of x, cos x, you can't factorise anything there. You could split it into two fractions if you want, so you can simplify the first one by cancelling out a sign, but it doesn't make things any simpler. So I just stop there, you're all done. Okay, example 2. Given that f of x equals e to the negative 2x times cos 3 of x. Okay, times cos of 3x. So you've got a product. Exponential times a cos, find f dash x. Alright, so product rule says that we differentiate the first function. So derivative of e to the negative 2x is negative 2e to the negative 2x. And we leave the second function as it is. And then we add, and we leave e to the negative 2x as it is, and we multiply by the derivative of cos of 3x, which will be negative 3 sine of 3x. Okay, so again, product rule, you quite often end up with common factors here, especially when you've got an exponential involved. We've certainly got negative e to the negative 2x as common, and then that is 2 times cos of 3x plus 3 times sine of 3x. So you can factor out that exponential if you want to tidy things up. Okay, part B, hence find the exact value of f dash at pi on 4. Okay, so we've now got f dash x, so f dash at pi on 4 is going to be equal to negative e to the negative 2 times pi on 4. And then in the bracket we've got 2 times cos of 3 pi on 4 plus 3 times sine of 3 pi on 4. And this is where this course starts to become difficult, because now, amidst your differentiation, we've used a product rule, which is a new thing. We've differentiated sine and cosine functions and exponential functions, and now we also need to know our exact values from our circular functions. So the fact that it starts to really bring everything together is what makes this such a challenging subject. So you need to be able to draw on all of those different aspects just here in this one question. Okay. So we know that cos of pi on 4 is 1 on root 2, and sine of pi on 4 is 1 on root 2. Okay, that's from your exact values, your special triangle, equilateral triangle, isosceles triangle with equal sides of length 1, which if you use Pythagoras makes that root 2, which means that sine, opposite of hypotenuse, is 1 on root 2, and cos of pi on 4, adjacent of hypotenuse, is also 1 on root 2. But we're not talking about pi on 4, we're talking about 3 pi on 4, which is in this quadrant. Okay, so we know that cos of 3 pi on 4, the x-coordinate, is equal to the negative. So I'm just going to, let me just tidy this one up while I'm here, so that's going to be minus pi on 2. So cos of 3 pi on 4 is going to be the negative of cos of pi on 4. In the second quadrant, cos is negative. Sine of 3 pi on 4 is going to be equal to sine of pi on 4. Okay, the y-coordinates in the second quadrant will be the same as the y-coordinates in the first quadrant. Alright, so we've got minus e to the minus pi on 2, then we've got 2 times negative 1 on root 2, plus 3 times 1 on root 2. Okay, so negative e to the negative pi on 2, and we've got negative 2 on root 2 plus 3 on root 2. So that is going to be positive 1 on root 2. So we've got negative e to the negative pi on 2, all on root 2. And you could rationalise that if you want, so it'd be negative root 2 e to the negative pi on 2 over 2, but there's no need to rationalise, so that's fine as it is. Okay, work for today is to focus on differentiation of circular functions, so that worksheet is in Appendix H of your booklet. In our next lesson, we'll start to bring everything together and do some mixed differentiation practice, so you can leave Appendix I for now, focusing on Appendix H.